stays this way. Right, so my name is YooJung, currently an assistant professor at ASU here. Although this semester I'm visiting the Simons Institute, so I've been mostly talking to the theoreticians all semester. So today has been a really nice change of pace. All the talks have been really interesting, so thanks to the organizers. So as the last speaker of the day, I have this privilege of standing between you and your dinner. So with that privilege, I would like to tell you about our work in this framework of probabilistic reasoning for trustworthy AI. So here's a rough plan. First, I'd like to tell you at a high level what do I mean by this framework and why in particular do we care about probabilistic reasoning here. And I'll, as an example, give a little bit of an overview of our recent work in applying this in algorithmic fairness. And then lastly, I'll talk a little bit about what's the key kind of ingredient, the backbone of this framework, which is trackable probabilistic models. Right, so diving in. So I don't think I need to convince this audience that we care about reasoning about AI and machine learning model behaviors. For example, we might care about how, when we make automated decisions, how fair are those decisions across demographic groups. You may want to explain why the particular decision was made, and also, how robust is that to, for example, when you have missing data or some distribution shifts. And a key thing to note here is that these issues, we want to study them together. We don't really want to study them in complete isolation because, for example, if you say that a certain model is unfair, you might want to get some explanations, maybe some example kind of patterns of bias, try to debug the model, or in the case of missing data or distribution shifts, you may want to provide guarantees that are actually robust. So the idea is that we want to develop a single framework that can handle these different reasoning problems. And another thing to note is that these properties such as fairness, for example, inherently depends on the kind of underlying population distribution of where you want to deploy the system. So these questions inherently end up being kind of probabilistic questions often. Okay? And same thing for example, robustness and other properties. So what we can do is use the language of probabilities and turn these tasks into probabilistic reasoning tasks. Right, so we have these questions involving probabilities and expectations over some distributions. So how do we actually compute these values? Well, we like data, so we might try estimating this from data. So one popular notion of fairness for classification that people have looked at is, okay, I have a predictor making some predictions across the population, and I want to see, is this predictor equally accurate for different demographic groups, for example, across different gender groups? So to estimate that, basically what you can do is, okay, look at your data, and then, so let's say these are two different gender groups. See, evaluate your classifier and then compare those accuracies. So this is simple enough, except that in practice, often the picture isn't this pretty. We may have labels that are biased, noisy, or missing. We might also have parts of the data missing, and other sources of uncertainty. Okay? We want to handle all of these different kinds of uncertainty, which is where the framework of probabilistic modeling and reasoning come in. So what we do is try to explicitly model the underlying distribution. Ideally, we'll learn this from data while kind of addressing these different sources of uncertainty, right? So we're really trying to capture what's the underlying distribution, perhaps with domain knowledge. So including prior knowledge or domain knowledge to address some uncertainties that's not apparent just from looking at the data. And then with that model, what we'll do is turn these trustworthy AI problems that I mentioned into a probabilistic inference task. So given some prediction model, so far we mostly focused on classifiers and regressors. And then this probabilistic model encoding this underlying distribution, we want to ask, okay, is this model fair under that distribution or robust under that distribution encoding these different uncertainties? And given those answers, what we also want to do is then use that to actually correct those behaviors and improve the prediction model. Right, so that's the main high-level picture. So what's nice about this is, first, once we can find a suitable model, this kind of suitable backend engine. So if we find a nice model and inference framework, this is a single machinery that we can develop to answer a lot of different trustworthy AI problems. So my group's kind of working on solving these different issues, as well as developing and studying different probabilistic models and inference algorithms. Today, I'd like to tell you in particular about actually auditing and enforcing fairness in the presence of noise or bias in your training labels. So let me first describe the setting. So let's say we have some training data with the target variables that we want to predict. Well, except often in practice, we are given some different set of observed labels that may not exactly be equal to the target variables that we actually want to predict. So one example is, imagine you're trying to make, let's say, like hiring or promotion decisions, and you're treating this as a prediction problem. So we want to predict someone's future job performance. So to train that kind of model, you might take some historical data of past employees and their review, performance review or promotion records, and then trying to predict based on those previous review records. Well, the problem is the true target, the job performance that you actually want to predict, is inherently latent, and this historical data might encode some historical bias. So ideally, these two should be the same, but often in practice, they're not exactly equal. They're correlated, but not exactly equal, and may have some bias encoded. This is an issue, well, first of all, just from prediction point of view, because we're not actually given the target variables that we want to predict in the training label. And more importantly, when we consider fairness, the issue is how do we even reliably audit or assess fairness of a given model when we don't have access to the true target variables. Like I mentioned earlier, a couple of popular kind of, fairness notions that people have looked into is based on this idea that the perfect predictor or perfect classifier should be considered fair. So based on that intuition, these models try to, or these notions of fairness try to equalize accuracy or precisely in this case, true positive rates or false positive rates across different demographic groups. Well, the problem is that if you're measuring these true positive or false positive rates with respect to bias labels, then the notion of fairness kind of falls apart, right? Because the intuition was that a perfect classifier should be considered fair. If you're perfectly predicting a bias label, clearly you shouldn't call that fair, right? So with this modeling and reasoning approach, what we try to do is actually from the data where the true target, which we assume to be fair, is completely hidden, and we're only given this bias label, we want to explicitly model the fact that there is a hidden fair label. Try to uncover that mechanism, right? Uncover the bias mechanism going from the hidden label to the observed labels. And given that model, we try to audit or assess fairness and also enforce the fairness notions with respect to these target labels that we infer using this probabilistic model. So going kind of at a high level, basically the key idea here is in the observed data, we have the features that we see, some sensitive attribute like gender or race and so on, and the labels, which again may be biased. So what we'll do in our model is, oh, by the way, I haven't told you what this is, what this model is yet, so don't worry about it. It'll come in the later part. But basically this, well, spoiler alert, this is exactly the kind of model that we use called probabilistic circuits. I'll tell you more about them later. So what we do is, in addition to the variables that actually appear in the data, in our model, we introduce another latent variable to explicitly represent this hidden fair label. Because this is just a latent variable that we introduced, it can be anything, so we have to tell the model what to do with it. So we will encode some group fairness notion, which for probabilistic classifier basically turns into some independence assumptions, some independence and conditional independence assumptions, which can actually be explicitly encoded in this kind of explicit probabilistic model. And once we have those properties enforced, what we'll do is ensuring that the fair label that we learned will actually satisfy those group fairness properties. We learn the joint distribution over all of these variables to actually best explain the data. Okay? So with this, we were actually able to show that we can uncover the underlying hidden fair label with fairly good accuracy. I'll show you actual results in a bit. But also using that model, we can go further. So what we can do with this is, for instance, if you're given some data with this kind of bias label, we'll learn this bias mechanism through learning this probabilistic model, and then actually output a clean data where we replace this label with the fair labels that we'll infer using the model. For that, it really just boils down to looking at each data point and then asking what's the probability of seeing a certain fair label given all the data you've observed. So this is computing conditional probabilities and then sampling from it. And what's nice about this is that now we have this data cleaning tool as a pre-processing step that we can now pass to downstream tools that will audit fairness according to different fairness notions, and also learn classifiers or regression enforcing those fairness notions. What's not shown here is also we can, if outputting or adjusting data is not available, as it is in certain applications, what we can also do is use this probabilistic model and modify these auditing or fair learning tools so that we can explicitly assess the expected fairness notions and also enforce those directly. So by expected fairness notions, what I mean is earlier I said that the fairness properties end up looking like equalizing some probability values, right? So now those probabilities will be respect to this latent fair label probabilities that we inferred and then encoded in the model. So with that, color's not really showing well here, but so with that, what we showed is first focusing on auditing, so focusing on estimating fairness violation of a given classifier. So what we saw is that compared to the ground truth fairness violation, so these green rows here, saw that using our approach of cleaning up the data and then using the inferred labels to estimate those violations got results that are much closer to the ground truth. Whereas if you just take the observed data and try to assess what the fairness metric would be for different classifiers, you usually end up being much more overly optimistic. So you underestimate what the fairness violation would be. So in this case, close to 0 is better, right? So you want to equalize in this case true positive rates between demographic groups, ideally closing down the gap to 0. So here you can see that using the observed data directly, you would often underestimate, or you would say your model is fairer than it actually is. And then actually using it for enforcing fairness properties during learning, what we saw is that you can actually achieve basically lower fairness violation while really still maintaining competitive accuracy. So in this case, we're comparing, so these are different classification methods. So this is just simple logistic regression as a baseline. These two are actually fair classifier learning methods. And what we saw is using the pre-processed data rather than directly on the observed data, we get fairness violations that are much lower, whereas the accuracy is still competitive, right? So what was underlying in this work was basically this mystery figure here, right? How are we actually getting this probabilistic model? What actually is this model? So let me tell you a bit more about that. Okay, so what do we actually need for this framework to work? In the example of this fairness work that I just told you about, hidden in there were many probabilistic inference tasks, including computing marginals, conditional probabilities, sampling from the distribution, and also learning from missing data. Right? We had a latent variable, so we want to be able to also learn probabilistic models where your data can have missing columns or missing features. What that means is, well, so that's the first challenge is we want to be able to compute these different probabilistic queries, and ideally in a exact and efficient manner. These were just some examples of inference we might care about in different problems. Different probabilistic queries will arise, and they may even be harder tasks. So ideally, whatever model we choose should be able to handle those queries efficiently. And then the second challenge is find the model that can answer those queries, but can still capture interesting distributions. And also encode and handle different uncertainties that I mentioned earlier. So for example, we also needed our model to encode some fairness constraints and actually satisfy it as a hard constraint. So we want a model that can capture interesting, complex underlying data distribution while being interpretable enough that we can massage it to, for example, encode some background knowledge or some constraints that we care about in the trustworthy AI domain. So putting that together, basically what we need is probabilistic models that are expressive, but still support efficient and flexible reasoning. Let me give a slightly more visual view of that. So these are the two X's that we care about, expressiveness and intractability. And let me kind of fill in this picture of what we have available in the space. So on this end here, we have these deep generative models, such as GANs, VAEs, diffusion models, and of course also autoregressive language models would also be around here, where these are very expressive. You can generate very realistic samples from them. But they're not much tractable, meaning you can't use them to answer a lot of different probabilistic queries efficiently. Right? We don't really know how to take a VAE and then ask, okay, what's the marginal probability from the distribution that you are implicitly modeling. Okay? So that's one end of the equation here. And on this opposite end, we have these tractable models, such as simple Gaussian mixtures, HMMs, or tree-structured graphical models, where we make some simplifying assumptions so that we can answer different probabilistic queries efficiently. Right? So we can compute marginal probabilities and conditional probabilities from these models efficiently. But then because of those simplifying assumptions that we made, so because those assumptions might not hold in the real world, they're less expressive. So really where we want to be is in this corner. We want to be both expressive and tractable. So that's where this mystery figure that you saw earlier come in. Is this framework of probabilistic circuits, kind of unifying many different tractable probabilistic models that exist in the literature. And the idea of these models is that you can be both tractable and they take some inspiration from existing tractable models, but increase expressiveness by essentially over-parameterizing them. And they can also be seen as kind of deep generative model with more structure that allows them to be tractable. So let me quickly tell you what these models actually look like. So pretty simple. You can think of them as a kind of weird kind of neural network or some computational graph that define distributions in a recursive way. Okay? So as a base case, we have the simplest univariate distributions. Could be Bernoulli. In the discrete case, could be Gaussian, Poisson, simple univariate distributions or densities. If we create mixtures of them, basically have these some nodes over some circuits or over some univariate distributions, these are also PCs. Here, PCs mean probabilistic circuits. We can also, in our circuits, have these product nodes that basically act like factorizations, right? So we're taking products of distributions. What's nice is now we have these ingredients, and all we have to do is stack them recursively to increase the expressiveness of this distribution or of this model, so that we can model more and more complex and interesting distributions. And I said that these are computational graph, basically to compute a probability of, given some inputs. All you have to do is plug in those inputs to your input leaf nodes. Just compute the products and weighted sums, following the circuit structure, and what it spits out is going to be the probability that you wanted to compute. Probability or density function. Okay? So these are explicit likelihood models that basically just tells you how to compute probabilities. And what's really the key here is not only are these explicit likelihood models, but actually by imposing some structure constraints on them, they let you actually compute different probabilistic queries efficiently, meaning polynomial time in the size of the model. And this will often be just linear time. To give you one example of that, we can compute, for example, marginal probabilities that came up earlier in the fairness work. If we have these properties on the circuit that basically makes every sum node behave exactly like mixtures, every product node behave exactly like factorizations, given those, we can compute any arbitrary marginal probability for partial assignment to any subset of variables just by a single feed-forward evaluation. All you have to do is just plug in the values that you're given. For any variable where you're not given a value, just replace that with the partition function in that leaf node. In the normalized case, this will just be replacing them with 1. And then again, just compute weighted sums and products. Whatever value it spits out is guaranteed to be the right marginal probability that you wanted to compute. Okay, so that was one of the 2 ingredients that I mentioned we needed. So the first one was tractable or flexible reasoning, right? Okay, so probabilistic circuits support that. We can compute, for example, tractable marginals, but by imposing different structural constraints, you can also show that you can compute harder probabilistic inference queries. And then the second part was, can they actually capture interesting distributions? So this isn't my group's work, but basically recent work has shown that these probabilistic circuit models can actually achieve better likelihood. In this case, these are all image data sets, so these are all measured in bits per dimension, which is basically proportional to negative log likelihood. The lower is better in this case. So these were shown to be competitive when compared against other deep generative models, known to be expressive, but are intractable, right? So these circuits can actually be competitive in terms of expressiveness while maintaining tractability. So a lot of what my group is working on is also trying to characterize the properties that will let us compute hard inference queries tractably on different models. Right? So we're trying to characterize what are the different conditions that you need to impose on the circuit to be able to compute some particular query tractably, and also show that, for completeness, show that when you don't have certain properties, these are actually proven to be hard. So we have some work that can, for some given query, automatically derive what are the necessary kind of conditions on the input circuits. So we have some example in this case for information theoretic entropies and divergences. I want to particularly highlight another query that is very related but slightly harder than computing marginals, which is basically computing expectations of arbitrary functions. So a marginal probability, you can think of it as an expectation where the function is basically just conjunction of some assignments to some of your variables. Of course, we can generalize this. Well, where is this useful? First, earlier, I showed that different fairness notions essentially boil down to equalizing some expectations. Also use this to make predictions when you have some missing values. So if you have a classifier regression function that cannot naturally handle missing values, what you can do is if we have a distribution over the feature space, then compute, okay, given some partial observation, what is the expected value of expected output of this function according to that distribution? And we show that compared to using imputation methods, we were able to achieve much, well, in this case, lower error across different percentages of missingness. And another kind of related way we can use this is also to compute the expected, essentially, robustness against missing data. So if, for example, in medical domain, let's say you're no longer able to run some tests, and you want to know, okay, how robust is my decision going to be when I'm making decisions with some missingness, taking into account the distribution over the tests that you will not be able to run. So looking at all the possible outcomes and the probabilities, what is the expected probability that your decision would change if you're making decisions with partial data? We can also use this for exploratory analysis of studying on different subpopulation. What is the expected output of my prediction model? Again, has applications in fairness, but also in general, just looking at studying kind of different behaviors of your prediction model. And then lastly, if this function is essentially a Boolean function, is a logical formula, then we can also look at, okay, what is the probability of some logical event happening in this distribution? So this could be about logical constraints, could be about some safety conditions. You can ask, okay, what is the probability of ending up in a kind of unsafe situation? You can even combine these and ask, okay, what is the expected behavior of my model conditioned on some obscure logical event happening? And we showed that if the distribution is given by a probabilistic circuit, and if the model is some simple model like linear model, decision trees and forests, and also another circuit that is discriminative or a classifier regressor, or another circuit including the logical formula. Basically, these are circuits consisting of AND and OR gates. So your classical logical circuit. Then we can actually compute this expected prediction in polynomial time. In this case, quadratic time to be precise. And we also have some approximate inference results in the case that your function is not one of these. So, hopefully, if you have some applications where you might be wondering, okay, like, what is the expected output of my model in some distribution or in some corner of your distribution, before diving right into, okay, let's estimate this from data, I would hope that you might first ask, okay, is this something that I can actually compute exactly? I think especially in trustworthy AI problems and in reasoning about model behaviors, if we can compute them exactly and provide guarantees, I think we should do so before jumping into estimations and approximations where we might lose some of those guarantees. Okay, yeah, so conclude, so I showed that we can model different trustworthy AI problems into probabilistic reasoning task with the underlying backbone coming from probabilistic circuits and the tractable inference that we can do with them. If you're interested in learning more about these models, we actually gave a series of tutorials. Most recent of which being at last year's NeurIPS. The slides and recordings are all available online, so you can check it out. Or, I'm also happy to chat about them later. And that's it. Thank you.